This next conversation is truly form following function. These speakers are founders with a personal connection to a problem. They've both seen they've seen their loved ones' worlds shrink because of mobility issues. And their mission is a world where nobody gets left behind. So they founded Skip and invented a new product category they call MoveWear. Their first product, Mogo, is the world's first pair of powered pants developed in partnership with Arc'teryx using AI-driven robotics built into apparel. Mogo delivers up to 40% power, a 40% power boost going uphill while absorbing impact on the way down. It's not a medical device. It's not bulky exoskeleton. It's a pair of pants. Kathryn and Anna met while working at Google X, where they spent years exploring how wearable robotics could support human movement. They saw a gap. Millions of people dealing with mobility challenges from aging, injury, fatigue, and no product was designed for them and felt like something you'd actually want to wear. Welcome.
Hi everyone, I'm Kathryn. Do you have a microphone? And this is Anna.
Hello.
And we're from Skip, and Skip is all about restoring joy to people through powered movement. And so Anna's wearing one of our first products here, which we'll talk about more in a second.
Awesome. So we started this project about 7 years ago at this point when we were at Google X. And the key premise, like Christine was saying, is this idea that movement is this incredible force in our life, right? It's the lifeblood in a lot of ways. It contributes to our physical health, our mental health, our social connection, you name it. It's a huge factor in that. And it's also really hard, right? Like this should look familiar if anyone was watching the Olympics a couple weeks ago. Even for the top 0.001%, it can be hard at times. And certainly for the mere mortals among us, it often starts hard and it usually gets harder with age, right? And so we like to poll the audience. We have a giant audience today, so we're gonna ask you guys to put your hand up if there's anyone in your life that struggles with movement. They can't move quite as quickly, quite as much as they would like to. And of course, that is what makes this a really fun and inspiring and impactful problem to work on, is because everyone's hand inevitably goes up. This is a fun statistic. A couple years ago, we kind of passed this threshold where we now have more people over the age of 50 in the world than under the age of 15. And this orange bar is growing. It represents about 2 billion people today. And so Kat and I often get asked, is MoveWear, is Mogo for older people? And it isn't always, right? But movement challenges a lot of the time do correlate with age. And so it's something we keep a close eye on. It's also one of the biggest predictors in mortality and just like health decline, right? It's just a huge, huge thing. And so we think it's really important. And if you look at the product landscape of the things that are available to someone who struggles with movement, it usually kind of looks like this, right? They're usually passive things that you sit on, that you lean on. And you guys can all read the slide, there's a lot of kind of downsides that we saw with that. And it also hasn't really changed, right? If you think about the past 20, 50, 80 years, it has largely looked like this. There's some cool innovation happening now with wheelchairs and braces, but we kind of got really excited about the prospect of not just something passive, but what if we actually put motors and batteries in products and actually help you kind of augment your ability in a more kind of active way. And so we're not the first people to think of this. I don't know if anyone has seen things like this. They're called exoskeletons. I'm actually kind of curious, has anyone ever worn an exoskeleton or tried one or seen one in real life? Yeah. Was it one of these?
I had a client about 15 years ago in New Zealand who developed an exoskeleton like the one on the right, but I think it weighed about 150 pounds.
Right, exactly.
You have to always be lowered into it.
Exactly. Yeah. So a lot of the technology has come from the military historically, and the main kind of pockets have been, designed for soldiers carrying hundreds of pounds for hundreds of miles. There's been a number of products in the kind of enterprise space, warehouse workers lifting very heavy boxes in very repetitive ways, trying to protect their bodies, and then also medical, right? A lot of the time people who have suffered a pretty serious spinal cord injury, so these are products, again, back to the Olympics. I don't know why I keep coming back to the Olympics, but a couple years ago, a bunch of you probably saw like the torchbearer wearing a full body exoskeleton, lighting the torch, and so these are all products that are, to your point, they weigh hundreds of pounds, they cost hundreds of thousands of dollars, so not exactly compatible with sort of a grandmother going to the store. And so we are Skip. As you guys know, we're developing MoveWare, so we're taking some of the more cutting-edge exoskeleton technology that we're developing, but we're miniaturizing it, and we're building it into products that we think are a lot more compatible with daily life. So we call it MoveWare. This is our first product, like Christine was mentioning. I'll just kind of very quickly explain what it is that you guys are looking at. So at the knee, I have a motor on both sides. There's a lever arm, inside of which there's a bunch of sensors. So we're going to spend a bunch of time, Kathryn will talk about the machine learning and the software. You know, people always look at the physical product, but a lot of the magic actually, of course, happens at the data and the software level. So we're going to get into that in a second. So every time I'm taking a step or I'm moving, the device is in real time trying to understand what is it that I'm doing, understand what kind of assistance would feel most natural, most intuitive, most impactful to me, and then delivering it with the motor. And then we often get asked, like, okay, well, so how does this actually go into my legs? Does it plug into my muscles? Does it connect to my nerves? It's very mechanical, right? There's essentially a carbon fiber knee brace that's just built into the pants. So there's a cuff back here, a cuff at my shin, and a cuff at my ankle. And so anytime the motor moves, that's actually what's kind of physically moving my leg. And just to give you an idea, if I'm going up a steep hill or a set of stairs, this gives me about a 40% boost to what my muscles can normally do, my quads and hamstrings, all the small muscles around my knee. Kind of feels like someone's walking behind you, pushing you under the butt, if you've ever done that. And then on the way down, it protects your knees. It takes the pressure off the knee joint. So rather than, you know, if you think about going down a set of stairs, rather than my back leg supporting my full body weight, the motor does a lot of that work.
I can tell you why we started this work. And so for me, this is a very personal journey, and I'm sure this is a common story where my grandmother was in her 90s, lived about a mile outside of her little village in Scotland, and she used to walk everywhere. She would walk to the shops, she'd walk to church, she'd walk to like flower arranging club, you know, all the cute things that like old ladies do. And then one day she had a fall, right? And she didn't necessarily lose mobility immediately, but she lost the confidence in doing that walk regularly. And then once you kind of stop exercising regularly, what you see is people often will start kind of a pretty rapid physical and then also social decline, right? So I think what surprised me is, once she wasn't confident walking, she didn't go to coffee, she didn't walk to the library, you know, all of the things that was her social fabric became a lot smaller. And so I was really motivated to think, how can we solve like this problem? And I think the irony, or what I found ironic, is that my day job at the time was leading a team at Google X. So these are some of the smartest people working on deep tech, working in robotics. And yet a lot of the problems that they were going after were kind of fun, interesting problems, but not things that would like affect as many lives as mobility and movement and the kind of things that we're interested in. This is my granny. And so it was while we were at X, we thought, okay, let's start an investigation looking at what would it be like to help people move. And I think in those very early days, we spent a lot of time talking to users and customers and understanding why they don't use existing mobility products. And we heard again and again things like, well, a walking stick or a walking frame is helpful, but it takes both hands. You know, so if I'm trying to go shopping or I'm trying to play with the grandkids, I don't want to be carrying around a stick. And similarly, you know, there are things that might sort of give you an alert if you have a fall. I don't know who kind of knows these products, a bracelet or a necklace. But that's kind of after the fact, right? Like I was like, no, I want something that prevents someone I love having a fall. It doesn't just send me a text message to say they might need help. And so we sort of started defining, okay, what does a successful product look like? And it's on body, so it's hands-free. It's powered, because then it can actually help you do the task you're trying to do. It's not just sending you an alert or giving you a notification. It's actually enabling someone like my grandmother or kind of our friends and family to be more active. And then it's also something that people are excited to wear. So, you know, my dad is now in his 70s, and he doesn't think he's in his 70s, so he doesn't want to wear a knee brace. He doesn't really admit to himself that he's got mobility issues, but he's got knee pain. And so he would be pretty reluctant to use what feels like a medical device, but he recently got an e-bike and raves about it, right? Because the e-bike is seen as something that grows accessibility and kind of expands your horizons and isn't viewed as a medical device. And so those are some of the principles that we kind of took into the early days at X of forming what this product should be. Does he need to log in? Oh, no, great. Okay. All of the problems we've just spoken about have existed for decades. So the one question is, why now? Like, why does it make sense to do this now and not before? And there's really two big things. One is the AI and the controls that I'll talk about in a second. But the other to touch on quickly is the hardware. And so, you know, this is kind of roughly the mass and type of structure that would be needed to deliver the same amount of, 40% of a person's body weight 20 years ago. And of course, it's like heavy and bulky. And it's both on the motor side, so the kind of actuation, and then also on the battery side. And actually, it's the drone industry very recently that's driven a lot of innovation in the kind of ultralight and very efficient actuators that then benefits us. So we can now do, in less than 2 kilograms, what would have taken kind of 6 before. And that's the difference between something that feels really heavy to 2 kilograms is not nothing, but it's much closer to a heavy pair of hiking boots or a pair of ski pants, kind of normal for the garment segment. Okay, so then the other big thing is physical AI. So I'm going to go deep and nerd out for the next 10 minutes, and then Anna will take us back to what makes this a good product. So when people think about physical AI, you often think about self-driving cars, robots, things like that. But there's a few key components. You normally have perception of the world. So you're using cameras or LiDAR or something similar to understand what's happening. There's then some reasoning component. Most of these are some version of kind of a vision language action model. So the perception will use computer vision to say this is an apple and a cup of coffee and something else. And then the reasoning model will say, well, my instructions were to clean up. That probably means put the cup of coffee in the dishwasher, right? And then action is kind of doing that task, right? So this is kind of typical physical AI and robotics. Here's an example in action. This is a figure humanoid. I think figure's amazing, right? So this is some of the most cutting edge technology in the space. And the instruction he was given was put away the dishes, uses computer vision, looks at the dishes, looks at the rack, uses a language model to identify what the action should be, and then does it. So there's a few things that are quite different about what we're trying to do. So let's take these step by step. So if you think about perception, if you're training on video data, if you look at all of the video data in the world, there's about 1 trillion hours of it. Now, only a tiny fraction of that is currently used for training, but there's tons of it. You can download open source models, you can download data sets, you can go on YouTube, and you can train vision models to identify objects, right? So this is a problem that kind of is relatively tractable for most of robotics. And then reasoning, if most robots are given instructions like clean the dishes, clean the house, put this over there, that's language-based instruction. And so they can use existing language models, which obviously a lot of people are investing a lot of time in getting very good. And then the interactions are typically with static objects, right? So the robot can very slowly and carefully pick up something, put it over here, tighten a screw, that kind of thing. We don't have any existing data sets, right? Because the kind of data that we need to train these models is data about how humans are moving. And that's hard enough. There's one level further, which is how the human responds to movement, or how the human responds to assistance, rather. Right? Because the last thing you want is for this robot to say, oh, let's help Anna stand up. But if she's not expecting it and then she resists or tenses or kind of pushes against the machine, that could be potentially dangerous. And so we have to do a lot of our own data collection to understand how humans are moving and then how they respond to different types of forces on the body. And then the kind of decisions that we're making are not like natural language decisions. These are decisions that are like, is the human stable in this moment, or are they at risk of falling, right? And okay, if the human is doing a movement that they need assistance with, should I apply a little bit of assistance or a lot of assistance? Should I kind of apply a lot of assistance, but it might feel a bit punchy? Or should I apply less assistance very smoothly? And these are not questions that are well suited to existing language models. And then to make life even harder, our models all have to run offline. Because if you want to take this hiking or to the supermarket, you can't send a query to the cloud and then wait for ChatGPT to come back with an answer. These are often instantaneous decisions, particularly something around, say, balance. This has to happen immediately offline. And then you're not kind of slowly working with a set of static objects that you're moving around. You're applying forces on a real human. So as I mentioned, there's a lot of interacting with the human in real time, being adaptable, and it's kind of a cooperative set of actions. Just to highlight how critical this is one of the most dangerous situations for us. So this is maybe an older adult who's trying to go downstairs, and he might be a fall risk. Now, that first step of stair descent, if you get that wrong, if you don't know that he's going downstairs, and you apply a force that he's not expecting, you could cause a fall, right? So this is much like the self-driving cars. It's these are very dangerous kind of decisions to be making, and the stakes are really high. On the other hand, if he's expecting support, because as we said, we support people going downstairs, and you don't provide any support because you're not sure he's going downstairs, that could also trigger a fall, right? So these are kind of very high-stakes decisions, and much harder than being able to take a minute and have the robot think through a bunch of reasoning. It's no, you have to know as the human's taking the step what they're doing. I also like this analogy where it's it's not like a human's getting into a car and then the car does all the work. It's more like the human is kind of on a horse, and our robots are kind of the horse in the situation where there's a lot of dynamic interaction, and we're getting signals from the human maybe saying, oh, I'm going to go left, or I'm going to give some kicks to the horse, but it's much more of a kind of cooperative relationship than it is, okay, I'm now relinquishing 100% of control to the robot. It's another reason that this category of robotics is also harder than the big exoskeletons. So the big medical ones often have a pre-programmed like walking controller, and the robot does 100% of the walking and carries a human along. And that's great for someone with, say, spinal cord injury or full paralysis, but not a fun experience for anyone who's used to having a bit more autonomy. But this is a much harder problem. Okay, so we're trying to do a hard problem, is what I'm trying to say. And then it gets even harder. So I want to kind of step through some examples of what we might think about for chips in particular that are doing this AI inference and the model work. So this is like a classic data center. So that's what's going to be doing your large language models. This is an example humanoid robot. And this is our product, right? So then let's think about what kind of compute is in each of these. So these are just examples from the categories. But here's like one of your hefty data center chips. They're big, and they're $20,000 a pop. This is what's in a couple of the leading humanoids. They're still kind of 10 centimeters by 8 centimeters, kind of pretty big. $2,000. We're trying to get products where the entire product is $2,000. So we can't be spending just that on a chip. This is the kind of chip we do our inference on. So it's a centimeter by a centimeter, and it costs $20, right? So it's a huge difference in scale. And the other reason is it's not just the size of the chip, but you've got to think about how power hungry they are. So these guys use the data center chips use about 700 watts, which is normally on mains power, but if you need to think about it, you need about 30 kilograms of battery to last 8 hours of powering that chip. A humanoid robot for 8 hours, it's about 50 watts, you need 3 kilograms of battery. Something like a big e-bike battery, and you can sort of imagine most of the chest of these humanoids are battery. Our chips, you can run them the entire day on the equivalent of a AAA battery. And so that's the main reason we have to go to these small, lightweight chips, because again, we're trying to keep the weight of the whole device really low. But what that means is, compared to a data center chip at 4,000 tops, or a humanoid robot at kind of nearly 300, we have less than 1 top of computing power. So we're trying to do a more difficult problem offline with 500 times less computing power, which is kind of mad, right? Like, this is a hard problem, and that's part of the reason why these haven't become really mainstream yet. Or you might see some kind of flashy demos, but having something that feels responsive and where people will trust their life to the product is a really high lift. Okay, so then let me spend a little bit of time talking about how we're doing this. So firstly, this is the leading biomechanics lab at Stanford. This is the robot that actually one of our PhD graduates built during his PhD, so I can flag it off and know that it's friends and family. This makes sense if you're trying to do exoskeleton research, right? Because you're measuring lots of things, you can control lots of degrees of freedom, and you've got a treadmill where you can get a steady state walking speed. But this is not how real humans move, right? This is one of our users on a trip, right? This is overground terrain. This is not steady state. These are complicated steps. And so the jump from steady state laboratory kind of academic work to having a product that functions in the real world over varied terrain is pretty difficult. And this is maybe too much in the weeds, but here, this is kind of knee angle. Hopefully you can see these slides. Here, what you see is someone who's climbing up a flight of stairs. They stand still for a few seconds and they keep going. And this is a model that's trained on steady state data, and it's terrible. Like, if you can't see the slide, the answer is that the predictions are all over the place and they don't follow the ground truth. So what we're doing in an individual moment, each line is kind of a forward prediction of where the body's going to go, where the knee's going to go, and we're predicting very poorly. This is a model that's only trained on 6 minutes of data, but it's 6 minutes of data that includes the exact thing that we're doing, which is someone climbing some stairs, standing, and starting climbing again. And our models are much better at agreeing with the ground truth. So the takeaway here is that you need not just varied data, but you need to have almost every movement that you might see in the real world kind of in your data set, and that gives you much better agreement than if you only train on treadmill data, or maybe you train on treadmill and a stair climber. But if you never have any of these transitions, if you never have kind of real world movements, you're not going to be able to identify and predict them in the real world. So we partnered up with Georgia Tech, and we collected the world's largest data set of varied movements, right? So again, traditional data sets have been treadmills, steady state walking, maybe stairs, maybe sit-to-stands. We did more than 50 non-cyclic movements, is really important, so it's non-kind of repetitive, including things like lifting and skipping and like calisthenics, which is a whole range of things, right? And so we tried to get really good ground quality data for what the body is doing in these huge variety of movements. And the slide will say kind of biological torque. That's kind of the torque that's happening in your legs. So again, we're understanding what you as a human are doing in these movements. We then supplemented that with hundreds of hours of people using our products in this real terrain, right? And what we're often doing is we're trying to forward predict, is this step going to be a step downstairs or a step over a rock? And what's nice is after someone has taken the step, you know what they actually did, right? So you kind of have good self-labeling of data over the long term. And basically that means that we can do it. So all this chart shows is the ground truth and then the predictions following each other for something like incline walking that's regular, but also for weightlifting. So again, weightlifting is a kind of non-cyclic, unusual movement, but we have very good agreement between what we're predicting the kind of biology is doing using our models and what's actually happening in the body. And then just to show you that in real time, this is someone walking around the lab in one of our kind of older exoskeletons. And then in real time, we're estimating what his joint forces are doing. And you can see it's continuous and smooth. So we're not swapping between a finite number of states. Instead, we're giving continuous estimates for how much torque his body is producing in a variety of movements. So you can see kind of squatting there is kind of high torques, but it's continuous and seamless across these different movements. That also means you can get to things like playing basketball, which would not be anywhere remotely possible with your old schema of steady state activities. So basically we have this like nice data flywheel. So although we can't leverage a lot of existing data, the more users we have, the more data we collect, the better the models get. The better the models get, the stronger the value proposition is, because your accuracy goes up and your confidence goes up. And this will be especially important, and is one of the reasons we started with hiking. That might even be the next slide. We started with hiking for Mogo because you get a lot of that varied data, which means that by the time we're advertising devices for the elderly, for fall prevention, for stroke, we will have had almost every type of weird sidestep movement you could imagine and have a lot of confidence that we've seen everything before. Okay, so that's like one half of the problem. So now we know what the user is doing, right? So that's like the perception half of the problem. The second half of the problem is, okay, well, how do we decide on the action? Like, what is the right amount of assistance to apply in any given situation? And the naive thing to do is to just say, well, we know what the biological forces are doing, you could just copy that. And that's fine, but it's not optimal. And there's a lot of studies to show that actually you can do better than just copying your biological forces, because often you might want the force to kick in a little bit early to kind of help you on the hard bit of the problem, for example. But it's a hard question, what is optimal in this case? So, Anna's going to come back to this framework later, but the top here is kind of what makes a good product. It's got to be usable, it's got to be comfortable. But the most important thing is it's got to be useful. And when we ask users kind of what's useful, you get a variety of answers, and absolutely none of them are related to what the academics in the exoskeleton world focus on, which is metabolic cost. So there is a bunch of like good research out there which does human-in-the-loop optimization, where they'll put people in these respirators and they're measuring your kind of oxygen output, and they can understand how much energy your body's doing, and then they can run this through an optimizer, and they can kind of personalize assistance to provide the optimal assistance for reducing your metabolic cost of transport. And that's great, and it's like a nice, easy-to-measure statistic. But what you end up producing are forces that are really high, because, of course, what you end up doing is trying to say, well, let's have the body do as little of its own work, and the exo does like the maximum work, and it feels terrible. Like, these are really uncomfortable controllers that come out of these optimizers, because it's often very high torques, very suddenly, kind of like maximum. And this is not how any of our customers think about what like optimum assistance is. Instead, we hear a variety of things, but we hear someone might care about balance, or they might care about pain reduction, or maybe they do want kind of reduced effort, but subject to it still being comfortable, right? So not these kind of very strong forces. And so one kind of concept that encapsulates all of this is just to ask users what they want. So to be like, what's your preferred kind of type of assistant for these steps. And so we do a lot of this. And again, we do some of this in collaboration with academics. And this is an example of, this over here is a grid where each dimension is a different parameter in the exoskeleton. So you could just imagine this might be how quickly your torque comes in and how much torque you get for a particular step. And we'll have users who will walk on a treadmill, this is treadmill work unfortunately at the moment, at a particular incline, and let them play around, let them pick different points on the grid and experience what these different torques feel like. And so, don't worry about the top at the moment, but this is how much torque someone is getting during a steady state movement. And you can see as they pick a different point on the grid, they're getting wildly different amounts of torque and shapes of torque. And one example of this is some people really like having their knee picked up, having like a little bit of flexion torque here to like help them clear over an obstacle. And other people hate that feeling. They're like, that's distracting, I don't want it, I don't have issues with kind of foot clearance. And so sometimes these negative torques are like helping you lift, and then kind of positive torques are kind of pushing you off. And so we can let users explore this space, and you end up with, hopefully this loads, like a preference landscape. So you can say for an individual user, what's their preference score for various like parameters in the controls. But what's tricky about that is that's only 2 parameters in the model. And these are machine learning models. There's many parameters that go into defining how much assistance we provide. And so instead what we prefer is something like this is an algorithm called rank CMAS. It's a little bit of machine learning on top of some of this work. And you do A/B tests. So now we can give users a few A/B comparisons. Hey, do you prefer that feeling or this feeling? And use that to, over time, kind of optimize what their preference is. So the tricky thing is, at the moment, this takes a little bit of time. So we'll have a user walk on an inclined treadmill, and using a laptop kind of press what they prefer and try different things. And it takes 20 minutes to kind of converge to, okay, now we know what your preference is. What we're currently working on, but I can't share because it's not public yet, is if we do enough of this data collection, can we get to a point where we can predict someone's preference just in how they walk, right? So this has never been done before because the academic data sets are often 5 people, like 5 grad students doing an algorithm. And we're trying to do this with hundreds of people so that we can say, oh, I can tell that you walk more slowly, you drag your foot a little bit, you're probably going to prefer this type of algorithm versus, oh, like you're walking quite fast, but you look like you have knee pain because I can see your left side is a bit slower, you might prefer this kind of algorithm. So the hope is that long term, we don't have to do any of this preference work. Instead, we can measure a user's gait as they're walking and predict their preference off the bat. At least for the majority of users. It's likely that someone who's a niche medical user might benefit from doing 5 minutes of A/B testing to kind of fine-tune if they have a very specific gait pattern. I think that's near the end of kind of the nerdy AI section anyway. So I'll hand back to Anna, but I think the final thing to say here is all of this is the hard part of what we're doing, and yet ideally users never comment on it, right? Like when we take people out and they have a good experience, they never say anything about the controls. They'll say, oh, that felt great, that helped me climb, like I have less pain. You only ever notice the controls when something doesn't work, right? It's like, oh, it was a bit jerky, or oh, it missed that step. And so over time, it's like we want the hardest part of the problem to be totally invisible to the users.
All right, so we do a lot of work on the software, on the controls. We have the best possible algorithms. Everything is feeling amazing. But will anyone actually want to put this on day in and day out and use it, right? And so, Kathryn was mentioning some of the humanoid robotics. Obviously, it's one of the hottest areas right now. Billions of dollars are going into this space, and there's a lot of amazing things that are happening. And most people in this room are probably at least somewhat excited about the promise that they hold, if not fully. But probably a lot fewer people are excited about going on a hike with one of these robots on their back, right? And so kind of the things we wanted to talk about from a product standpoint today are how do you minimize friction? How do you design for behavior change? And actually, part of at the core of what we're doing is we're helping people move with more ease, with more joy, and hopefully move more over the years, right? So that inherently implies a change in behavior to some extent. How do you invest in trust? And then how do you position this as something aspirational, right? Something that people actually want to wear, not just something they need to wear. And so from a friction standpoint, product adoption really is just value minus friction, right? Kind of like what Kathryn was saying. you need to be useful, right? You need to be delivering value and benefit, otherwise no one will ever wear the product. But even if you build the most useful thing ever, if you don't minimize the frictions, if it's not reliable, if it's not comfortable, if it's not lightweight, if it's not usable and doesn't look good, it kind of doesn't matter, right? And so we spent a lot of time from the very beginning, in the early days, thinking about how do you actually quantify these frictions and how do you minimize it for a product like Mogo and some of the, excuse me, MoveWare products that we're building. And in the early days, we kind of like to think of users as being part of our design team. Even in the early days at Google, we would spend hundreds of hours with people in the field trying to understand what is it that you would want out of a product like this if you could wave a magic wand. And a lot of the time what we heard is, I want this thing to be invisible, right? And this is not uncommon in the assistive device space. I, before this, worked in hearables and hearing aids, and again, it's something you hear all the time, right? It's like, yeah, I feel like I maybe need to use this product to move in the ways that I want, but I don't want to detract attention. I don't want this to be a conversation piece. Like, please just hide it, right? Make it invisible. And so we kind of entertained that through a number of prototyping. And before baggy pants were hip, we kind of ended up with something that looked like this, right? Like, you see what I'm wearing? There's just like physics behind it. The motors are as big as they are. The batteries are as big as they are. And so we try to minimize it. But if you were to fully hide it, you would end up with something that looked like this. And the interesting thing is, some people wanted to hide it, but everyone wanted a really usable product. And as you can imagine, if I was wearing a pair of overpants on top, I wouldn't be able to see the LEDs, I wouldn't be able to control the device up or down, turn it on or off, I wouldn't be able to take the batteries or the motors off, swap batteries as I was walking. So there's just a very big usability tax. And so that was kind of very core in the early days, is like, you don't actually want it to be invisible, you want it to look good, right? And it was a big kind of reframe for our team and how we approached it. It's why we partnered with Arc'teryx for the first product and kind of really shaped our product roadmap. The other thing is behavior change, right? Like, this probably describes some of us. A lot of people buy gym memberships and never use them. And so, again, we're all about equations here today. But if you think about behavior change, the most common framework is, there's a trigger, there's something that prompts you to do the thing. There's action, like what are we actually asking of users every time they put the product on? And then what is the reward? Like, what are they actually getting at the end of it? And so if you think about the trigger, the way we think about it at Skip is, how can we piggyback as much as possible on existing behaviors, right? I put the slide in, and Kat and I were in the Uber today, and we were just like counting the people on the rental bikes whizzing past us with no helmets on. We all know that we should wear a helmet, but of course, if we're out and about and we don't have the helmet with us in the moment, it doesn't really matter, right? We just don't do it. And so for us, for MoveWare and for Mogo, what that's really come down to from a product standpoint is building MoveWare into clothing, right? It's not just something you have to carry around all day so that eventually when you need it, you put it on and use it. How can we actually integrate it into the thing you already have in your closet, the thing you've been putting on for years and decades, and just kind of augment rather than replace? From an action standpoint, right, like, you really do need to make it 10 times easier than you think you do for people to use it. One of our team members, kind of has a limb difference and has many prosthetic arms. And it's a really great example that we like to come back to, because prosthetic arms, you would think it gives you this incredible thing, like it literally gives you a limb back, and yet about 50% of prosthetic arms go unused, right? And it really is because they are heavy, they're clunky, they take too long to put on. It's really kind of like a usability rather than a capability problem. And so we take this really near and dear. We try to make sure that the product from start to finish, as you take it out of the box, it takes less than 10 minutes to put on. There's very minimalist UI, right? Like, everything we do is in the name of having this thing just fade into the background as your day goes on. And I often have a lot of arguments with our engineers. They're like, well, does it really matter? Like, what if it takes 4 minutes to put on? Like, would we really not ship a product if it takes 4 minutes to put on? And like, of course, it's not about any one of those things, right? It's about the aggregate. But we kind of take this really, really seriously as kind of the controls and software that Kat was talking about. And then the reward, right? Like, just making it sure that once you've done all that, it actually feels worthwhile to you every time. And so, there's been plenty of products that have been novel and exciting and then just go unused. And so for us, that kind of comes down to both making sure that it feels useful instantly out of the box before the machine has had time to learn about you, your preferences, your behaviors, your gait. And then making sure that it gets better with use, right? It learns about your walking style, your preferences over time, and every time you put it on, it performs better than it did the time before. Trust is another really big thing we think about from a product standpoint, and like, these are other mobility examples, but Waymos are everywhere in San Francisco, and I remember the first time I went in, I was a little bit scared, And then 5 minutes into it, I kind of forgot that it was a robot driving the car, and I was on my phone texting my friends. And so these technologies we kind of take for granted a lot of the time now, but they took decades to get there, right? Like, it is very natural to be afraid of something like this, and whether it's cruise control or self-driving cars or autopilot or some of the medical devices we have, it just takes time. And it'll take a while for people to feel like this is, second nature. But there are things that we can do to kind of ease consumer trust. And so the things we think a lot about at Skip are transparency, predictability, and control. So transparency from the very beginning, right, is very challenging, because if you think about it, the only output we really have on this device is a set of LEDs, right? And so that can tell you how much battery life you have left, it can tell you how much assistance you're getting, and it can also tell you if something's going wrong, but that's kind of it. And yet the user really wants to know what's actually happening. And so we think a lot about how do we actually take machine state and translate into human understanding, right? Like, what does 60% of assistance really mean? How much work is it doing for me? The other piece is predictability. And so I always kind of like to say that predictability trumps raw performance. And what Kat was talking about really kind of underscores that, I think. A lot of the time, our engineering team wants like the most responsive, the most, fill in the blank, the most performant controls. But that can feel more jerky, and a little jerkier is actually sometimes a lot worse than predictable. And so we really kind of, as we think about how do we push the software forward and the controls, we think about kind of conservative behavior and graceful degradation to make sure that you're sure that when you put the device on today, it's going to behave exactly like it did yesterday and the day before. And then finally, control, right? Like, there's a lot of things happening in the background on the software level and at the controls level, and we want it to all be smart and automatic and seamless. But we want to make sure that if something ever does go wrong, the user is undoubtedly always in control. And so the way we designed it, this is actually the old prototype, but the battery is very analog, it's easily removable. At a moment's notice, you can cut power to the device, and that kind of is that. All of the attachment points to the body are completely analog, so at any given point, you can kind of flip the switch and turn things off. And so the last thing kind of is, when does tech stop being assistive and start being aspirational, right? Like, a lot of the things we talk about at Skip is, yes, we're designing products a lot of the time for the people that need them, quote unquote, but we also want to make sure that they're wearing them because they just want to, right? Like, they're excited to get them in the mail, they're excited to take them out of the box, they're excited to show them off to all their friends. And so we take inspiration from a lot of other product categories. In my mind, glasses are like still the token, like the poster child for this, right? When you put a pair of glasses on, it's helping you with a very functional and assistive need, but it's not really kind of it's also very much a fashion statement, right? Like, you don't just wear them because you need to see, you're kind of telling to the world, this is who I am. And a lot of the time that comes down to choice, right? And so Kat and I a lot of the time get questions like, oh, there's other exoskeleton companies coming on the market, are you guys worried? And like, absolutely not, right? It's like a huge, huge problem space. There's billions of people who need help moving. And the fact that you and I might choose a different version of moveware or a different version of an exoskeleton is an amazing thing. And I think it gets us closer to this. So that's kind of the what. The other really important piece is when you show up in a person's life. And so we like to kind of talk about continuity, not crisis, right? I think the Apple Watch, I don't know how many people are wearing Apple Watches, probably a bunch in the audience. I think this is a really great example, right? Like, a product shows up in your life, and the core product might stay the same over the years, but the features that you know and love and rely on very much kind of change, right? And so it might start off with fitness tracking, and then it might evolve to heart health and maybe fall detection. And so we kind of take that very much to heart in how we design our product also, trying to earn a place in someone's daily life early on and kind of become more and more valuable as the years go on.
Great. And so then, that's kind of all been really about Mogo, which is this first product. But at Skip, we're trying to build out a platform of devices, right? So what we envision is a world where no one's left behind. And we started with examples around grandparents or sports accidents or like a huge variety of movement. And so the goal is to be able to take a lot of the hardware components in this kind of a product and a lot of the software infrastructure and controls that we've developed, and then over time build out different applications. And so the hardware might end up with a slightly different look and feel, but maybe it reuses the actuators, the motors that are kind of one of the most tricky components, or maybe we reuse the chips, etc. And the other products that we've been doing early work on are things like Parkinson's disease. And Parkinson's has very little in common with hiking, but that's kind of exactly why we picked it. We wanted to pick something where it was at the other end of the spectrum. It was a more medical device. And people with Parkinson's often struggle with gait on a daily basis, right? They kind of struggle to take big steps and kind of follow through. They're also a fall risk. And falls are something that has a lot of universal it's a universal challenge as people get older. And so those are kind of the two things that we're starting with. And then from there, hope to build out really an ecosystem of products so that whatever your movement challenge is, there'll be something that will help you and meet you where you are in that journey. Yeah. I think that's all from us. Do we have any time for questions?
We have 2 minutes. Can we see it in action? Can we see you move?
I mean, it's been on, yeah.
Yeah, this is basically it. So essentially, it's like as you sit down or stand up, the device supports you.
It's helping you get back up. It's helping you go down and back up.
Yeah, and from a sit to stand standpoint, we like to talk about a lot of the time if someone is, struggles with mobility challenges or knee pain, or a lot of the time they kind of do this, they kind of plop down.
Yeah.
And so this kind of helps you sit down in a more controlled fashion and pushes you back up. And same thing on a step. I mean, there's no steps to demonstrate with, but anytime you step up, it helps you kind of extend.
Yeah. Any questions? We have time for one, maybe.
Yeah, thank you so much for the presentation. Touching on your last point about like Parkinson's patients, I know they suffer a lot from steady state tremor, where they tend to shake a lot, and this affects like their shuffling. While skip is an exoskeleton, could there potentially be a use for rehabilitation, where like eventually they won't need the skip anymore because they've come to a point where they have functional independence?
Yes. I actually think maybe less so for the Parkinson's example, because that's by definition degenerative. But we think about it a lot for, say, someone who's had knee surgery. And at the moment, you're in a very restrictive knee brace until one day you're not. But it's like, obviously, the body heals more slowly. And so you can imagine a product like this, which initially provides a lot of support after surgery, and then over time provides less support and kind of eases you out in a more natural transition. And so, I think there are certainly rehab examples. The other thing strategically is, as a small company, we've started with like the non-regulated, non-medical product, because there's so much to learn about the controls and the user interfaces. But we have partners lined up and are kind of going through the process of looking at what is the knee pain device, what is the rehab device, what is the Parkinson's device. But they'll likely take more time, because it will also take more time to prove that you can bring someone back to full health after an injury. Yeah, exactly.
Okay, let's I'd love for everyone to kind of see and hear it, but maybe that can move to the side and outside so that people can, because I heard it and it definitely, you can see the support even though you're not physically feeling it. So we want to thank you. It's incredible what you're working on, and it's really going to change lives. Thank you. Thank you, guys.
Thank you.